We talked about ionic compounds earlier in the course, and we'll visit them again later when we talk about reactions. In the solid state, ionic compounds crystallize in what we call ionic solids. We'll introduce some more cubic unit cells and find that they're related to the 3-unit cells we saw with metals. Ionic solids are held together by ionic bonds. We know from Coulomb's law that the stronger the interaction between oppositely charged ions, the lower the energy. So cations and anions will arrange themselves to maximize the plus-minus interaction. Since cations and anions are different sizes, packing efficiency is also a concern. On the left is a diagram of the face-centered cubic unit cell we saw in the previous module. The atoms touch along the face diagonal, and we note that there is void space along the edges of the cube. On the right is a diagram of lithium iodide. Note that the iodide ions, shown in yellow, maintain what we would recognize as a face-centered cubic arrangement, which is an efficient way to pack spheres. The lithium ions, shown in green, are much smaller than the iodide ions and can fit into the void spaces. Here are two other alkali metal halides, lithium chloride and sodium chloride. Again, the chloride ions, shown in yellow, appear to keep the familiar face-centered arrangement, with the lithium and sodium ions again occupying the void spaces on the edges of the cube. Since sodium is bigger than lithium, the chloride ions have to move farther apart to accommodate the larger sodiums. The gap between the yellow spheres in lithium chloride is smaller. We might be tempted to call this a face-centered unit cell, but this arrangement is actually a new unit cell. It is called the sodium chloride unit cell, sometimes referred to as the rock salt unit cell. What happens when we have two ions that are close to the same size, as in cesium chloride? In these pictures, cesium is orange and chloride is again yellow. The illustrator has drawn this in the traditional way with the larger ions at the corners, which in this case is cesium. On the left, we have the orange cesiums in a face-centered arrangement and the yellow chloride ions on the edges. In this case, the packing efficiency is rather poor, and the orange ions on the face have to separate a significant distance to fit the yellow ions. If all the spheres were the same color, we might actually mistake this for the simple cubic arrangement, with a coordination number of 6, which we know has a poor packing efficiency. Rather than adopt this structure, cesium chloride prefers to adopt the structure on the right. Although we might mistake this for a body-centered cubic unit cell with 1 yellow sphere surrounded by 8 orange spheres, since the sizes of the two ions are different, this is a new unit cell. We call it the cesium chloride unit cell. This is the 5th unit cell we have seen based on a cube. Here is our chart. We can now go down the right-hand side with ionic compounds. They crystallize in ionic solids. The smallest unit is the ion. As we've stated before, with ionic compounds, there are no molecules. The force that holds the ions together is what we have called the ionic bond, the attraction of cations and anions.